It is 2:51 in the morning when the evergreen Ever-a-Lot crosses the outer harbor. She is 400 meters long. Her beam is 61.5 meters. She is carrying 23,992 20-foot equivalent units, containers stacked 11 high above her deck, arranged with the precision of a solved equation. Her draft at this load is 16.1 meters. That means 16.1 meters of steel hull below the waterline, moving through water that is, in places along the approach channel, only 18 meters deep. The clearance beneath her keel, less than 2 meters. A harbor pilot boarded her 12 nautical miles out. Not a guest, a specialist, someone who has navigated this approach 3,000 times and still checks the tide table twice before boarding. He knows that the Fraser River discharges fresh water into the Strait of Georgia, creating layers of different density, haloclines, that affect how a vessel at this draft responds to rudder input. He knows that at certain tidal windows, a 400-meter ship does not steer the way its captain expects. He has compensated for that before his coffee goes cold. 2 tugboats are already running parallel, 5,200 horsepower each. Their lines are not yet attached. This is escort only, for now. But they are positioned. If the vessel's propulsion hesitates, if a rudder hydraulic falters, the tugs close the gap in under 40 seconds. The cranes are waiting. There are 6 of them on berth 4 at Deltaport, where each one is 80 meters tall at the peak of its boom. Each one is capable of lifting a 65-ton container from a vessel deck, moving it laterally 60 meters, and placing it on a truck chassis, repeatedly, continuously, with a cycle time of 90 seconds per box at peak efficiency. They have been calibrated for this vessel's exact container positions since 1400 yesterday, when her manifest arrived from the shipping agent. The ship is expected. The cranes are ready. The harbor pilot is bringing her in. The Port of Vancouver is the largest port in Canada and the 3rd largest in North America by total cargo tonnage. It operates across a geography that most port systems would consider unworkable. 28 marine cargo terminals scattered across 600 kilometers of coastline and waterways, connected by a river system, a tidal strait, and the logistical nerve tissue of 40 kilometers of on-dock rail. In a single year, the port moves approximately 170 million tons of cargo: grain, coal, potash, sulfur, automobiles, lumber, and containers, 3.6 million TEUs annually, representing a cross-section of Pacific trade that touches every continent. To understand how Vancouver works, you have to stop thinking of it as a single location. It is a system of systems. The kind of operation where a decision made in a dispatch office at Roberts Bank affects a rail departure in Kamloops 4 hours later, and which affects a warehouse receiving window in Chicago the day after that. Every link in the chain is load-bearing. Every delay propagates. The people who manage this understand it the way an engineer understands a structure under stress, not with alarm, with attention. Deltaport is the primary container terminal. It is built on reclaimed land at Roberts Bank, a tidal flat on the southern edge of the Fraser River Delta, 35 kilometers south of Vancouver proper. There was nothing here before 1970. As the land was constructed, dredged material from the approach channel deposited over years to build a platform above the tidal flat, then armored with rock, compacted, paved, and fitted with the infrastructure of a major marine terminal. The approach channel itself, 14.4 kilometers long, dredged to 16 meters below chart datum, requires continuous maintenance. Silt from the Fraser River settles. Currents shift the bottom. Every year, a maintenance dredging removes millions of cubic meters of material to keep the channel at depth. If the dredging stops, the channel shallows. If the channel shallows, the largest vessels can't enter at all tidal windows. If the tidal windows narrow, the terminal loses berth productivity. It is a maintenance dependency that never ends. The cranes on berth 4 are ship-to-shore gantry cranes, STS cranes in the industry shorthand. They ride on rails embedded in the berth apron, parallel to the vessel's side. When a ship berths, the cranes are positioned to align with the hatch covers, the large steel panels that seal each cargo hold. The hatch covers come off first, lifted by the crane, and set aside on the apron. Then the work begins. A crane operator sits in a cab suspended at the end of the boom, 55 meters above the berth apron. The cab is climate-controlled. The view downward is through reinforced glass. It is assisted by cameras that give direct sightlines into the container stacks. The operator controls the spreader, the rectangular lifting frame that descends on cables, locks onto the corner castings of a container, and lifts. Each container weighs between 2 and 30 tons depending on its contents. The crane's rated capacity is 65 tons. Headroom for the heaviest loaded units with margin. The operator does not guess at the weight. Every container on the vessel's bay plan is pre-declared. Gross weight, hazmat classification, temperature control status if it's a reefer unit. That information is in the terminal operating system before the ship arrives. The crane operator sees it on the cab display. The automated stacking crane in the yard knows where each box is going before the STS crane lifts it. The coordination between those two machines, STS crane and yard crane, is managed by software. But the STS operator is the pacemaker. Their cycle time sets the rhythm for everything downstream. Below the berth, the water tells a different story. The berth structure at Deltaport is a concrete deck supported on steel piles driven into the seabed. The piles go down 30 meters in places. The underside of the berth, the space between the water surface and the concrete soffit above, is dark, confined, and accessible only by boat or by dive. Poor marine maintenance divers work this space on a rotating inspection schedule. The inspection intervals at a port of this activity level are set by regulation and by engineering judgment. Piles are inspected for corrosion, marine growth, physical damage from vessel contact. The concrete deck soffit is checked for cracking and spalling. Fender systems, the massive rubber and foam-filled cylinders that absorb vessel contact at berthing, are examined for compression damage and structural degradation. Visibility under the berth is low, typically 1 to 2 meters. The water here is a mixture of harbor water and Fraser River outflow, cold greenish-gray carrying silt and debris. When a vessel is maneuvering nearby, the propeller wash churns the bottom sediment further. Divers working during active terminal operations must account for this. A sudden prop wash event from a tug repositioning can reduce visibility to 0 in under 10 seconds. The dive supervisor maintains radio contact with terminal operations throughout every dive. No surprise movements without notification. The divers know the system. They have to. The rail terminal at Deltaport is the arterial connection between the ship and the continent. On-dock rail means containers never leave the terminal on truck before going to rail. They are lifted from the vessel, moved through the yard by automated stacking cranes, and delivered directly to a rail car on the terminal's on-dock track. The train assembles on site. It departs when it is full, typically 200 to 250 containers, representing a train length of 2.5 to 3 kilometers. Canadian National and Canadian Pacific, now CPKC, both operate at Vancouver. Their main lines run east through the Fraser Canyon, through the Rockies, across the prairies, and into the distribution centers of central Canada and the American Midwest. The timing between ship discharge, container movement through the yard, and rail departure is managed to the hour. A container that misses its train departure waits for the next service, typically 12 to 24 hours. In a supply chain where a manufacturer in Ohio has scheduled receiving appointments based on vessel estimated time of arrival, a 24-hour delay has real downstream cost. This is why the crane cycle time matters. This is why the yard crane automation matters. This is why the harbor pilot's approach timing matters. Every decision connects. 3:47 a.m. The Ever-A-Lot is fast to the berth. Lines forward and aft, springs deployed, vessel made fast with 14 mooring lines, which each rated at 120 tons braking load. The gangway is deployed from the terminal side. The shore power connection team is already moving. Shore power, a cold ironing in the industry term, means connecting the vessel to the terminal's electrical grid so the ship can shut down its auxiliary engines while at berth. A large container vessel running auxiliary diesel engines consumes 5 to 10 tons of fuel per day at anchor. Shore power eliminates that. The electrical connection is made through a standardized cable bundle. Thick, heavy, water-resistant, deployed by a small crew working at the vessel's waterline access point. The shore power cabinet is rated at 6.6 kilovolts. The connection takes 45 minutes. Once complete, The vessel's engine room goes to minimum operating status. The terminal is now powering the ship. That is a logistical reversal that most people don't consider. The port, for the duration of the vessel's stay, it is not just processing the ship's cargo, it is also sustaining the ship's electrical systems. The hatch covers are off by 4:15, 6 cranes working simultaneously, each crane assigned to specific bays, the numbered sections of the vessel's deck and holds. The discharge sequence is planned by the terminal's planning department the night before. Which containers come off first, in what order, to which yard blocks, assigned to which trucks or rail slots. The plan is not guesswork. It is a solution to a logistics optimization problem with thousands of variables. Which containers are for local delivery, going straight to truck? Which are for transshipment, arriving on this vessel and departing on another? Which are temperature-controlled, requiring connection to reefer power points in the yard? Which are hazmat, requiring segregated storage positions? Get the sequence wrong, and you can strand a container behind other containers that need to come out first. And the crane has to rehandle. Rehandling costs time. Time costs money. It slows the vessel's departure. A delayed departure may miss a tide window. A missed tide window costs a day. The planning team works with a system called a vessel stowage plan, a digital 3D model of the ship's container positions, updated in real time as discharge and loading progresses. They run scenarios before the ship arrives. They rerun them if conditions change. They have contingency plans for crane breakdowns. The vessel shifts at the berth, container weight exceptions. Not because things always go wrong, because when they do, the plan is already written. The yard. Behind the cranes, the terminal yard at Deltaport covers 170 hectares. It is managed by automated stacking cranes, ASCs, that move on rubber-tired wheels between rows of containers, stacked 5 high and 8 wide. The yard is divided into blocks, each block holding hundreds of containers. And the ASCs do not have operators in the traditional sense. They are remotely supervised from a control room inside the terminal building. Operators monitor multiple machines simultaneously, intervening when exceptions occur. A container that's been misidentified, a position conflict, a mechanical fault. The routine work is handled by the machine. The judgment calls are handled by the person. This is a significant operational shift from the manually operated yards of 20 years ago. An experienced straddle carrier driver from the 1990s could move 15 to 18 containers per hour. An ASC, properly optimized, handles 25 to 30 moves per hour, continuously, without fatigue, without shift change delay. The transition required retraining the workforce, not eliminating it. The new roles are different, less physical, more systems-oriented, more focused on exception management and equipment oversight. The machines handle the repetition. The people handle the unexpected. At 6:20 a.m., a reefer container in yard block F7 throws an alarm. Temperature set point, minus 18 degrees Celsius. Actual, minus 14. The refrigeration unit on the container has lost efficiency. The contents, 22 tons of frozen seafood bound for a distribution center in Toronto, have been holding temperature for 11 days since loading in Busan, South Korea. They have margin, but not unlimited margin. The reefer technician on duty gets the alarm on his handheld terminal. He is at the container within 8 minutes. The fault is a condenser fan motor, a replaceable component. He has the part on his service van. The repair takes 22 minutes. The container temperature stabilizes at minus 17.5 by the time he signs off the work order. The seafood arrives in Toronto within specification. Nobody in the distribution center knows any of this happened. Well, that is the definition of operational success in a port environment. The intervention that never becomes visible to the end customer. By 9 o'clock, the Ever-A-Lot has discharged 7,400 containers. The loading sequence has begun. 9,200 export containers, grain products, lumber, manufactured goods, potash from Saskatchewan, are moving from yard to ship in the reverse sequence of the discharge plan. Each one is lifted by the STS crane, swung over the rail, lowered into the vessel's hold or onto the deck, and positioned precisely by the crane operator using real-time bay plan guidance. The vessel's stability is recalculated continuously during loading. A ship is a floating structure. It has a center of gravity. Add weight incorrectly, too high, too far forward, too concentrated on one side, and the vessel's stability is compromised. The ship's chief officer monitors the loading computer, a real-time calculation of righting moment, trim, list, weighing shear stress on the hull. Loading a 400-meter container vessel is a structural engineering problem that resolves itself only when the last container is secured and the numbers confirm the vessel can handle the open Pacific. The chief officer signs off on the stability calculation. The master reviews it. The harbor pilot, when he boards for departure, will review it again. Everyone checks the numbers. One, because the numbers matter in a way that only becomes obvious in a storm 3 days out of port, when the vessel is rolling 15 degrees in a swell and every container on deck is a weight on the end of a lever arm. The Fraser River. The Port of Vancouver operates not just at tidewater terminals, but 150 kilometers up the Fraser River, to the port's inland container transfer facilities at Mission and Pitt Meadows. The Fraser is a tidal river for its first 100 kilometers. Its tides reach as far inland as Chilliwack under certain conditions. This means the navigable channel shifts with the tide, that vessel drafts must be calculated against tidal predictions, and that certain vessel classes can only transit specific sections of the river during high water. The river channel is not uniform. It migrates. The Fraser carries enormous sediment loads, the product of 234,000 square kilometers of mountain watershed draining into a single channel. The river deposits this sediment as it slows approaching the delta. Shoals form in one season and shift in the next. Port of Vancouver's hydrographic survey team runs continuous monitoring of the river channel. Survey vessels with multi-beam sonar sweep the navigable sections on a rolling schedule. The data goes to the navigation desk within 24 hours. If a shoal has built up above the safe navigation threshold for a scheduled vessel class, the captain is notified. In the tidal window for that vessel tightens, the river does not cooperate with operating schedules. The operating schedules accommodate the river. The port operates 365 days a year. There are no planned shutdowns for weather in a commercial port environment. When a Pacific storm system makes the outer harbor untenable, winds above 45 knots, sea conditions outside the pilot boarding area dangerous, vessels at anchor wait. The pilot launch does not go out. Vessel arrivals are delayed. However, but the terminal does not stop. Cranes can operate in winds up to approximately 72 kilometers per hour before safety protocols require suspension. Below that threshold, operations continue. Rain doesn't stop a crane. Cold doesn't stop a crane. The operators dress for it. In winter, the Fraser River approach can experience freezing rain and ice fog. Tug operations continue with additional caution. Visibility on the approach channel is managed through radar and VHF coordination with the Marine Communications and Traffic Services, MCTS, the Canadian Coast Guard Authority that manages vessel movements in the Strait of Georgia. MCTS is monitoring the harbor continuously. Every vessel movement into and out of Port of Vancouver is tracked. Every deviation from a filed passage plan is queried. Every vessel that loses propulsion or steering in a restricted channel, and it happens, perhaps twice a year, triggers an immediate response. Tugs, Coast Guard, Harbor Authority. The system has redundancies built in layers because the approach channel has no margin for a vessel aground. Maintenance dredging is scheduled for this section of the approach channel this week. The dredge is a trailing suction hopper dredge, a vessel with drag arms that trail along the seabed, suctioning material into an onboard hopper. When the hopper is full, the dredge transits to the disposal site and pumps the material overboard. The cycle time for a full dredge load and disposal transit, approximately 6 hours. The dredge works around the clock, with vessel traffic managed around its position. A notice to mariners has been issued. Vessels using the channel know the dredge's position. MCTS coordinates the passing arrangements. The dredge operator has done this run many times. The material in this section is fine silt, easy to suction, mud easy to dispose, but the precision required to maintain the channel at exactly 16.0 meters below chart datum across a 14-kilometer length requires constant sonar verification. Dredge too shallow and you leave a shoal. Dredge too deep and you're removing more material than necessary, raising the cost of a contract that runs to tens of millions of dollars annually. Depth management in a navigational channel is not excavation. It is calibrated removal. No, the vessel turnaround time at Vancouver, the time from first line to last line, departure, depends on cargo volume and complexity. For the Ever-a-Lot, with nearly 10,000 container exchanges, the target is 36 hours. This is a compressed timeline for a vessel this size. It requires 6 cranes operating at sustained efficiency, the yard system absorbing and dispatching containers without bottleneck, rail departures executing on schedule, and the pilot and tug team ready at the departure window. When the Port Authority's Vessel Operations Center tracks every ship in the harbor simultaneously. Berth schedulers, experienced people who have typically worked marine operations for years before moving into planning, manage a calendar that looks 6 weeks out and recalculates in real time. A vessel that arrives early needs an available berth. A vessel that arrives late has displaced the vessel scheduled behind it. A crane breakdown on berth 4 may require redistributing cranes from berth 3. In every change cascades, the scheduler's job is to manage the cascade before it reaches the ship. 1430. The Ever-a-Lot is at 80% of her load. The remaining boxes are heavy outgauge units, containers longer than the standard 20-foot or 40-foot module, requiring special handling and exact deck placement because they can't stack conventionally. The crane operator on Crane 3 has been working since 6 a.m. He is 8 hours into a 12-hour shift. His concentration is unchanged. The outgauge units require manual spreader adjustment. The telescoping frame extended to match the container's length. This slows the cycle slightly, 110 seconds per lift instead of 90. The planning team accounted for this. The revised completion estimate has not moved significantly. He places the last outgauge unit at 1452. The crane moves back to standard containers. The rhythm resumes. The port's marine operations extend beyond containers. At the West Shore terminals, 18 kilometers away at Roberts Bank, bulk coal and petroleum coke are loaded onto vessels through conveyor systems that run from the railcar dumper to the ship's holds at rates of up to 10,000 tons per hour. At the Neptune terminals, potash from Saskatchewan's mines, 400 meters underground, arrives by rail and moves into vessel holds through a closed conveyor system that prevents dust exposure and product loss. At the Cascadia terminal, bulk grain, wheat, canola, specialty crops, is received from prairie rail cars, cleaned, graded, and loaded onto vessels that carry it to flour mills and food processors in Asia, the Middle East, and Africa. Each terminal operates as its own system. Each has its own maintenance program, its own equipment, its own specialized workforce. What connects them is the harbor itself, the shared waterway, the shared approach channel, the shared tug fleet, the shared pilot service. The water is the infrastructure that all other infrastructure depends upon. At 22:15, the harbor pilot boards the Ever-a-Lot for departure. The same person who brought her in, not always, but on this occasion, the same pilot. He reviews the stability calculations, checks the final draft reading from the berth staff, a measurement taken at 6 points along the hull, fore and aft and midship on both sides. The vessel is trimmed slightly by the stern as intended. Draft forward, 15.8 meters. Draft aft, 16.2 meters. The tide is on the flood. High water in 2 hours and 14 minutes. The departure window is now, and the channel is at maximum depth during the flood, giving the vessel maximum underkeel clearance on the transit out. He makes the call at 22:21. Lines singled up. The tugs connect. The stern tug takes the push as the bow lines are let go. The vessel pivots slowly in the turning basin, a 400-meter structure rotating around a point in the water. Anyone watching from shore would see it as glacially slow. The tugs are working at near full power. The harbor feels compressed. By 22:41, she is in the channel, heading outbound. The tugs release and turn back to the harbor. The pilot rides the vessel to the outer pilot station, boards the pilot launch in the open strait, and returns to shore. The Ever-a-Lot continues west. She will be at the entrance to the Strait of Juan de Fuca by 1:30, in the open Pacific by 3 o'clock, 17 days to Busan. One behind her, the terminal is already processing the next vessel. The Maersk Sentosa, 366 meters, 19,630 TEU, is inbound. Pilot already aboard. Tugs already running. The cranes are repositioned to berth 3. The planning team has had her manifest for 18 hours. The cycle does not pause. The harbor does not rest. Somewhere in the approach channel right now, a 16-meter draft vessel is being guided by a person who has done this 3,000 times and still checks the tide table twice. The tugboats are running. The cranes are calibrated. The containers are waiting. The system is already moving. In a full operating year, the Port of Vancouver handles 3.6 million TEUs through its container terminals. Each of those TEUs represents a container that was loaded somewhere, shipped across an ocean, discharged here, moved through a yard, placed on a rail car or truck chassis, and delivered to an end destination on a timeline measured not in weeks, but in days. Whereas the total cargo throughput, all commodities combined, approaches 170 million tons annually. The port generates approximately $10 billion in economic activity for the Canadian economy each year. These are the metrics of a system that works. Not perfectly. Systems at this scale do not run perfectly. They run because the people inside them, the pilots, the crane operators, the reefer technicians, the dredge crew, the berth schedulers, on with the divers underneath the wharf, understand the machine well enough to keep it running even when parts of it fail. The water does not stop moving, the tide does not negotiate, and the vessels keep arriving. Under this video, there's a subscribe button. It's a small action, but it helps keep stories like this afloat. Sakram, if these systems fascinate you, the quiet force of water held in place by engineering and discipline, subscribing simply means you want to see more of what operates beneath the surface.